Good afternoon. So first of all, thank you very much for joining this RILEM and FIB Youth Council webinar, and especially thanks to Niki and Thilo for inviting me to take part into this event. And as Niki already said, today it's my pleasure to share our work on elucidating the role of enforced carbonation and clinker reduction in PET fiber reinforced strain hardening cementitious composites. Let me start off. Perhaps many of you are already familiar with SHCC. It's a special class of fiber reinforced concrete known for its exceptional tensile strain hardening behavior, as you can see here. And it is made of actually fine-grained cementitious matrix, and it's reinforced with typically short, uniformly distributed polymeric fibers. And when we design these or bring these two components together, it transforms the concrete from brittle material into pseudoductile one. So again, as you see here on the right-hand side, once the matrix, which is brittle, cracks at this point, the fiber starts to bridge the crack and transferring the load across the crack flanks. In this way, the composite develops many fine cracks and continue to carry the increasing load whilst still allowing large inelastic deformations. This is the reason what gives SHCC its excellent tensile ductility, as you can see here, the strain capacities on the x-axis. And it also makes SHCC to absorb a lot of energy during this tensile loading, which you can imagine with the area under this curve. And this is what makes SHCC very attractive, not only for new construction, but also for repair and rehabilitation of existing structures, as well as for the strengthening of structures exposed to, let's say, extreme loading scenarios, such as earthquake, blast, or impact. However, despite all these advantages in mechanical performance and high ductility of SHCC, it still faces an important sustainability challenge, mainly because of its material composition. Due to its fine-grained nature of the matrix, SHCC often relies heavily on Portland cement content. And the fibers that we typically use in SHCC are high-performance fibers, so that means they're also very expensive fibers. So this brings the CO2 footprint from the cement and the cost coming mainly from the fibers to a very high level in SHCC. And that brings us to the key question, which I will address in this talk, is how can we make SHCC more sustainable from, let's say, environmental point of view without losing the performance, and also how we can make it more economical. So to answer this question, one way to make SHCC more environmental friendly is to rethink both parts of the composite. That means the binder as well as the short fibers. On the binder side, one of the promising candidates that we can use to design SHCC is limestone calcined clay cement, or LC3. The basic idea is simple. Instead of relying so heavily on Portland cement, we can start replacing it with calcined clay and limestone. These are very abundant resources, naturally available, and they are very low carbon materials. For example, the system you see here is called LC3-50. That means it only contains 50% of Portland cement, while the remaining is mainly calcined clay and limestone, and a small amount of gypsum that we add in the binder for proper sulfation. And what is really interesting is that with LC3-50, it's highly tunable. We don't really need to stick to, let's say, 50%. We can go even further. And in one of the studies linked here by the QR code, we developed many LC3 composites, reducing the clinker content all the way up to 25, meaning LC3 development of LC3-25. And we were still able to achieve 28-day strength of 25 megapascal with the water to binder ratio of 0.4. On the fiber side of things, we can move away from the high-performance fibers such as PVA and PE, which you typically see in strain-hardening cementitious composites, and we can go for PET fibers. They are very attractive alternatives. They are very widely available, and they actually come from the most common polymer families in the world, which is polyester. And another advantage is PET is also one of the most recyclable polymer these days around the globe. So apart from these advantages of wide availability and recyclability, the cost of PET is really, really low. So it's up to 95% more cost efficient than polyethylene fibers. But the issue is that if we look at the tensile response of these single fibers compared to what we typically use, which is PE, PET fibers have very low tensile strength as well as very low modulus, and they are highly compliant. You can see they deform at very low load levels. They start this plastic deformation, which is quite extensive deformation here. But that doesn't automatically mean they cannot work in SHCC. Again, another study here linked by QR, where we have shown that we can actually design PET reinforced SHCC using the micromechanics-based criteria which is needed for the strain-hardening cementitious composites. The major issue or more serious issue with PET is its durability in alkaline environments. Because cement-based materials are naturally highly alkaline, and this is really one of the main reasons why, despite of all these advantages of PET fibers, they are still not considered or not used in SHCC. Here, for example, you see on this left-hand side a study that we conducted where we put PET fibers in an alkaline solution of 12.5 pH for different durations. So here you see on top 7, 14, and 28, 7, 14, 28, and 60 days. And also we wanted to accelerate this degradation, so we also put this for different temperatures for 20, 40, and 60 degrees. What these SEM images show is a very clear degradation of the PET fibers as the temperature or the exposure time is increasing. Yeah. And this you can notice, for example, how the diameter of the fiber is reducing. Yeah. And also the surface damage, the pittings are easily visible in these images due to prolonged and accelerated aging in alkaline solution. And in the most severe condition, which was, for example, for 60 days at 60 degrees, what we saw was nearly complete disintegration of fiber. And here is the image of what the fibers actually look like after this exposure. So they were completely disintegrated. Now, what we also did was using the Arrhenius degradation law, we also tried to model what is the effect of this degradation on the load-bearing capacity of these single fibers. And the model revealed very alarming results. And here, for example, you see that after this different aging process, the prediction suggested that PET could lose half of its load-bearing capacity within 120 days, which is the point here. And it can lose 90% of its load-bearing capacity within, let's say, a little over the year, which is the point here. Now, from performance, but also sustainability point of view, it's not really desired because we just don't want to use cheaper or greener material just for the sake of using it. We also want to maintain the function of what we design over time. So, and here you will see the reason what causing this kind of degradation is basically the alkaline hydrolysis process. So here, for example, if you see these PET fibers, they are attacked by these hydroxyl ions, and that destroys the polymer structure into monomers, for instance, to the ethylene glycol and to the terephthalate acid. And this ethylene glycol dissolves, but this terephthalate either forms the film around the fiber, but for longer, if you just continue the exposure, this high alkaline exposure, they start to precipitate as small crystals. And the effects are clear. Yeah, there's peeling off of the fibers, there's pitting, there's surface roughening, we lose the diameter and we lose the mechanical performance. So the next natural question is, what can we do about it? Can this issue be addressed? And the answer is actually, yeah. And I will show you two paths for addressing this issue. First is we can reduce the alkalinity of the matrix. Yeah, this is the, let's say, the most obvious way that we can go on about. Since the matrix alkalinity is closely linked to the Portland cement content, what we did in our study is we systematically start reducing the clinker content in the matrices. And here you see the three design matrices that I will show further in the upcoming slides how PET performs in these three matrices. So essentially what we are doing is cutting clinker content from 50% in LC350 to LC335, where the clinker content is 35%, and in the last we just use only 25% of Portland cement. The remaining portions we replace with calcined clay and limestone at a constant ratio of 2:1 by the weight of binder. And to make these matrices for SHCC, we of course add quartz sand, some admixtures for tuning the workability and stuff. Now to see the effect on the alkalinity of the matrix, on the right-hand side, what you see is some of the samples that we prepared. We cut it, and one phase we spray with dimophthalene, the top one, and the other phase of the same sample we sprayed with phenolphthalein indicator. And here you see how the color change with these two indicators works. So basically, phenolphthalein shows a light pink color between the pH range 8.2 to 10, and it becomes darker when you go above this range, and it remains colorless below this range, while dimophthalene has slightly higher but overlapping range where it shows light coloration between 9.3 and 10.5 and dark coloration beyond this and remains colorless. And again, if you look at these top pictures, you see LC350 and LC335 shows dark color, while LC325 shows very light color with dimophthalene. And this is the same case with the phenolphthalein indicator. So at least for LC325 here, we can conclude based on these indicator results that the alkalinity level in this matrix is somewhere between 9.3 and 10.5, which is quite lower considering for pure Portland cement, these alkalinity levels can be around 13.6. The second pathway we explored was enforced carbonation. The idea was to lower the matrix alkalinity after early hydration so PET fibers would survive longer. And a useful side effect of doing this CO2 introducing enforced CO2 in the matrix is that it doesn't just stay in the system as gas. It actually interacts with the cement phases, forming calcium carbonate as stable phase. So that means chemically bounding. We are trying to chemically bound the CO2 inside the matrix. Hence, in this way, we can sequester CO2 while bringing the pH down. So here is the scheme of how we cured the sample. At first, we cast the samples for compression, single fiber pullout, and tension test. And after 1 day of in-mold curing and 4 days of normal curing according to these conditions, what we did was we dried the samples for 1 day at 40 degrees centigrade, which we wanted to carbonate, a set of samples. The other set kept in for normal hydration in the standard lab curing chamber. This drying we did was to open the pore structure so CO2 can penetrate deeper. And after the 1 day, what we did was we carbonated the samples according to these conditions for 1 additional day. Once this was done, we took all the samples, whether carbonated set or the non-carbonated set, and we put it in fork chamber for an additional 14, 28, 60, and 90 days. And the conditions in the fork chambers were 100% humidity and 40 degrees centigrade temperature, because we wanted to see the effect of this accelerated hydration afterwards. So if there is degradation, so that we can notice it better. And after these curing times were concluded, we took out the samples, and the carbonated one, again, we cut the specimens and we did the indication, the phenolphthalein and dimethylene indicator test again, and here you see the results. So first thing you notice is that LC350 and LC335, they were not fully carbonated. Because the Portland cement content is high in these matrices, they are naturally denser materials. So the carbonation condition that we applied for all three, that means we need a harsher or a bit more stronger conditions, let's say, for these matrices to fully carbonate. While LC325, it has very low clinker content and its microstructure is not so dense, CO2 could easily enter and carbonate it fully. Looking at the color, so you see the shell around this non-carbonated core, it's almost colorless. Yeah, and that means the pH is below 8.2, even in this high alkalinity matrices after carbonation. While LC325, which is fully carbonated, yeah, it's shows colorless. That means the pH in all the system where you don't see color is below 8 or 8.2. Now let's go one step further into quantifying, let's say, this carbonation depth. So what we did was we took this cross-sectional areas and we tried to measure, let's say, quantitatively how much the area is carbonated and how much it remains non-carbonated. And here you see, for example, the results of LC350, which was, again, non-carbonated, just hydrated. And of course, here you see everything, the whole cross-section is just non-carbonated, shown by these purple bars. Also LC335, because it was non-carbonated, yeah, it shows, yeah, the complete area is non-carbonated. But what's interesting is this non-carbonated LC325 matrix. Although we did not carbonate it intentionally, after taking out from fog chamber and before testing it, the time it was sitting in the, let's say, lab environment, it started to naturally carbonate. And you see here the percentage areas of how much it was carbonated naturally. On the bottom, what you see is all the sets of samples that we intentionally tried to carbonate. And as I mentioned, 50 and 35, since they were denser matrix, they did not fully carbonate, but a large portion of the area was carbonated. So here on average, yeah, 40% was non-carbonated, 60% area was carbonated. And here on average, I think almost 14 to 15% remain non-carbonated, while the remaining 85% was carbonated. And LC325, due to its low microstructure density, it was fully carbonated. The scatter you see due to this different age, should not be overinterpreted as an age effect, because all the samples were carbonated at the same time under the same conditions. It is more likely due to the heterogeneous nature of the composites, which naturally leads to some specimen-to-specimen variation in the carbonation depth. Now, if you look at the right at the compressive strength, the first clear observation is that the non-carbonated samples generally showed higher strength than the carbonated ones. That makes sense because the blended cements, such as LC3, the hydration and the pozzolanic reaction leads to formation of cache phases, which are the most dominant phases in the blended cements. And when CO2 interacts with this cache phases, so CASH phases, basically it decalcifies and destroys this dense network, causing increase in the local porosity wherever the CO2 interacts with this cache phases, and the strength can drop. And another trend that you see is that LC350 shows high strength compared to LC335 and LC325, and this is because we are reducing the clinker content significantly over these three formulations. At the same time, the difference between, let's say, the carbonated and non-carbonated, yeah, it's also very interesting to know that the difference here is clear, that the carbonation is leading to loss in strength, but here it's not really clear, because when we try to crush the LC350 and 35 samples, since they are not fully carbonated, the core is the one that is strong and in the middle, so that is leading to a lot of resistance when we try to crush under compressive load. Now let's take a look at the tensile properties. So I will start off with LC350 composites. So what we will look at is the strain hardening behavior and the crack bridging response of these composites. Here, you can see that the stress strain curves, which are shown here, at different ages. So for 14 days, 28 days, 60, and 90 days, the blue envelope shows the samples that were hydrated, and the red envelope shows the samples that were carbonated before this prolonged hydration in fog chamber. I also drew the guidelines to mark where the average tensile strength and the tensile ductility of different composites lie. So if we focus on first on the blue envelopes, we can see that the non-carbonated composites still show very good tensile strain hardening behavior with multiple cracking at 7 days, so which is the case here. However, this performance gradually declines with increasing age, so you see here. And at 60 and 90 days, basically the tensile performance is next to nothing. So it's just very porous matrix remain because PET fibers degrade so heavily, like they dissolve in this alkaline pore solution of the matrix, leaving these channels empty and causing high porosity and leading to such worsening of the tensile properties. In contrast, when we look at the red envelopes, we can clearly see that carbonation allowed these composites to retain their tensile performance across all ages. So all these 4 ages, we can see how the tensile performance was preserved. And it's basically because the alkalinity is reduced quite significantly, and which is beneficial for basically mitigating the alkaline degradation of PET fibers. However, the tensile strain hardening behavior is not so prominent here or not so desirable here because there's not so much multiple cracking and not so much ductility arising even after carbonation. And to go further into why this happens, I will show you the results of this 90-day specimen. So what we did, we looked at the fracture surface and we saw that you can see PET fibers in the area where the CO2 could penetrate and reduce the alkalinity, but the core where CO2 couldn't reach, the fibers were almost invisible, at least to the naked eye. Also, we did the single fiber pull-out bond, and the effect of, let's say, carbonation to mitigate PET degradation becomes very much prominent here. And this is for the 90 days results. You can see for the carbonated, the fiber bridging or the bond between the fiber and matrix was preserved almost entirely, while the samples that were non-carbonated, they lost their fiber matrix interaction. This is the results of LC3-35. Because this matrix is inherently less alkaline naturally, you see the degradation is also slow in this. But still, the blue, the non-carbonated samples still degrade, while the carbonated samples show that they preserve the whole response. And this is also visible in the single fiber pull-out test. And lastly, I will show you the LC3-25, and this, as I mentioned earlier, this is naturally, the alkalinity levels are so low that you see the blue curves, which are non-carbonated, preserves a very good strain hardening response. In this case, actually, we don't need to carbonate because carbonation, as you've seen, reduces the compressive strength, opens more the microstructure, leads to more weakening of the microstructure. So here, carbonation is actually detrimental to the mechanical properties. So in this case, we don't need to carbonate for accelerated aging. For prolonged aging, the normal hydrated LCC25 shows sufficiently good strain hardening performance. And this brings me to the conclusion slide here, and I will conclude using the two perspectives. One is from the matrix design, and we can say that the highly alkaline LC350 matrix leads to progressive degradation of PET fibers, diminishing strain hardening behavior at later ages. However, the low alkalinity LC325 matrix maintains stable tensile behavior of the composites and did not lead to any PET degradation. From the carbonation standpoint, the carbonation curing effectively mitigates the PET degradation, lowering the alkalinity and preserving the fibers. And it's actually necessary to carbonate the high alkalinity matrices such as LC350 if you're using PET fibers to protect this. But in low alkalinity matrix, carbonation should be avoided. And this brings me to one of the last slides here, where I would just like to acknowledge and thank everyone for their kind attention. And before closing, I would also like to say that I'm really grateful for the German Research Foundation, DFG, for funding the research training group GRK 2250, in which I conducted this work. But also, I would like to acknowledge the Cluster of Excellence CARE, Climate Neutral and Resource Efficient Construction, as well as this use project. And finally, I would like to sincerely thank RILEM and FIB again for giving me this opportunity to share this work with all of you today through this webinar. If you want to read more, you can check out this paper, which was based on this work that I presented today, and you can also connect with me. Thank you very much.
So hello, everybody, and thank you very much, the 5E Young Members Group and also the RILEM Youth Council for the invitation. In my presentation today, I want to present some aspects related to the structural application of fiber reinforced concrete, mainly focus on the new provisions incorporated into the Eurocode 2, and together with some practical consideration of the application or real application of the fiber reinforced concrete in actual structures. This will be more or less the small index that I'm going to follow. So I'm going to start, well, just to have this framework or about the codes and the designs provision. I want to say that in Europe, I'm going to focus on Europe. Structural standards are developed within the CEN, the European Committee for Standardization, which is the responsible for the development and harmonization of the technical standards across European countries. Within this framework, the Eurocodes constitute the common basis for structural design in Europe. Currently, the Eurocodes include 9 Eurocodes together with the Eurocode 0, which is related to the basis of the structural design. And in the case of the concrete structures, the corresponding standard is the Eurocode 2. These Eurocodes are developed within the CN through the Technical Committee 250, dedicated to the structural Eurocodes only. And each one is developed by a specific subcommittee. In particular, the case for the concrete structure, the Eurocode 2, is currently chaired by Alejandro Pérez Caldetel from the UPM in Spain. So the new generation of the Eurocode 2 has already been published and delivered to the national standardization bodies, and it's expected to be officially adopted by the member states in 2027. One of the more relevant aspects of the new Eurocode 2 is the incorporation of several annexes related to the new materials and technologies. And among them, the Annex L is the one which specifically addresses steel fiber reinforced concrete structures. This is particularly important because it represents the first time that a comprehensive design provision for structural steel fiber reinforced concrete have been incorporated directly to the Eurocode. Also, in parallel to the Eurocodes, the FIB has played a fundamental role in the development of structural concrete design provisions. The current FIB was officially created in 1998, and after the merge of the SEP and the FIB, two organizations who has already collaborated for decades in the well-known SEP-FIB model codes. This evolution finally led to the FIB Model Code 2010 and more recently to the FIB Model Code 2020, which was published in 2024. In many aspects, the current Eurocode provisions for fiber reinforced concrete are strongly connected to the previous developments carried out with this FIB framework. Regarding fiber reinforced concrete, the FIB Model Code includes a broader approach than the current Eurocode 2 because it considers different types of fibers. It includes steel, polymerical, glass, or carbon fibers. In particular, Model Code 2010 was probably the first major international document providing a relatively complete framework for the structural design of fiber reinforced concrete. And at this point, I would like just to briefly mention my own involvement in this field. I participate at both national and international level in different standardization and technical activities related to fiber reinforced concrete. At national level, I'm involved in the Spanish task group dedicated to the practical application of Annex L of Eurocode 2, and internationally, as Thilo mentioned at the beginning of the webinar, in the FIB Commission 10 on model codes, particularly within the task group 10.3, where I'm currently coordinating the working group 3, focused on the design or making examples of the application of the design for fiber reinforced concrete structures. So starting from the Eurocode perspective, I want to introduce some main concepts and assumptions that currently are considered for the structural design of steel fiber reinforced concrete. So the first thing I want to share is that the Eurocode 2 is mainly based on the previous developments from the FIB Model Code 2010, the German DAF STB guideline, and also on national recommendation and practical experience from the different European countries. The document explicitly considers steel fibers as a structural reinforcement capable of replacing or complementing conventional reinforcement. In this regard, fibers are mainly used to enhance the residual capacity of the composites after cracking. Actually, in compression, fibers improve confinement and ductility, while in tension, they contribute to crack control, energy absorption capacity, and the post-cracking residual strength. From the material point of view, one of the key aspects is how residual strength of fiber reinforced concrete is experimentally characterized. So the residual, this property, the residual behavior of steel fiber reinforced concrete, is indirectly characterized through the 3-point bending test defined in the EN 14651. The test consists of a notch beam subjected to bending, where the applied load is related to the crack mouth opening displacement, or known as CMOD. And based on this test, the residual flexural tensile strength corresponding to different cracks openings can be determined, particularly the characteristic values FR1 and FR3, which are associated with the serviceability and ultimate limit state respectively. It's important to say that this residual strength depends not only on fiber content, but also on parameters such as the fiber orientation, distribution, and also the bond between fiber and matrix. So based on this residual strength, what makes the Annex L is classify the different fiber reinforced concrete according to the strength and ductility. So the classification proposed in the Annex L is based on the characteristical residual strength obtained from the 3-point bending test, particularly the characteristic values FR1 and FR3. So the strength class is defined according to the characteristic value FR1, while the ductility class depends on the ratio between the characteristic value FR3 and the corresponding strength class. As it's shown in the figure, this classification allows distinguish between materials exhibiting softening behavior and materials showing hardening behavior after cracking. So about design assumption, since the material characterization is based on flexural test, Annex L provides simplified approaches to derive equivalent uniaxial residual tensile strength for structural design. So in this regard, two characteristical residual strengths are defined. One is associated with the serviceability limit states, another is associated with the ultimate limit states. So these design residual strengths are obtained considering several correction factors, namely the fiber orientation factor and also the member size factor. The fiber orientation factor accounts for the fact that the fiber distribution and orientation in the actual structure may significantly differ from those obtained in the standard laboratory beam test. So in practice, fiber orientation is strongly influenced by casting procedures, concrete flow, member geometry, or the placing conditions. So for this reason, Annex L allows, for example, the orientation factor to be experimentally assessed through representative tests performed on the real structure. Actually, in the example that you see, in this experimental campaign, a full-scale steel fiber reinforced concrete flat slab was tested up to failure, and afterwards, cores were extracted from the slab and were analyzed using inductive techniques to characterize the fiber distribution and orientation within the structure. But Annex L also considered the influence of the structural size on the variability of residual properties through the member size factor. So this allows considering a more stable structural response in large scale members. So now let's continue with the constitutive law for the materials. In compression, what proposed the Annex L is that the constitutive law remains relatively similar to that of the plain concrete, although fibers contribute to increasing the ductility and energy absorption capacity of the material. For this reason, there are modifications in the compressive strain corresponding to the main compressive strain and the ultimate compressive strain. But the main difference appears in tension. In this case, Annex L proposed a simplified three-linear constitutive law, which is capable of reproducing the post-cracking response of the material, including either softening or hardening behavior depending on the residual strength class. So the effective value FT1, as you can see in the screen, corresponds to the characteristic value associated with the service residual strength, while the effective value T3 is obtained based on a moment equilibrium of the notch cross-section. And finally, about the design assumption related to durability, it's true that Annex L adopts a relatively conservative approach. Actually, the minimum cover required for durability is generally considered unaffected by the presence of steel fibers. This means that any potential durability benefit associated with the inclusion of fibers is neglected in the code provisions. Nevertheless, steel fiber reinforced concrete surface layers are still vulnerable to deterioration. So since steel fibers close to the exposed surface may be subjected to corrosion and may potentially lead to rust straining effects, for this reason, Annex L introduces an additional consideration based on the concept of sacrificial layers, where the tensile contribution of fibers close to the surface is disregarded in the structural verification. Well, once the material assumptions are defined, Annex L provides a specific provision for both ultimate and serviceability limit state. Let's see the most important ones. So, for example, for bending, at the ultimate limit state, Annex L proposes simplified constitutive models to represent the residual tensile behavior. So two approaches are considered, a rigid plastic behavior or a bilinear behavior in tension. In practical, the contribution of fibers is introduced by introducing the sectional analysis through residual tensile stresses acting below the neutral axis after cracking. And in compression, the same stress block approaches used for reinforced concrete may still be considered, although modifying the compressive strength parameters to account from the increase of ductabilities that fibers give to the concrete. If we talk about the shear, steel fibers contribute by controlling the opening and propagation of inclined cracks generated by shear. So instead of developing a single critical crack, steel fiber reinforced concrete members tend to exhibit a more distributed and stable cracking pattern, which improves aggregate interlock and enhances the shear transfer capacity across the crack section. So within Annex L, the fiber contribution is introduced through an additional resistant term associated with the ultimate residual tensile strength. And at the same time, the code introduced this reduction parameter, eta, to account for the fact that the fiber contribution is not fully additive to the concrete or the reinforcement contribution. As shown in this experimental campaign, the reduction of the cracking pattern in members with fibers may become very, very significant. If we jump into punching shear, there are several experimental studies that have confirmed the beneficial effect of fibers on both punching shear strength and the formation capacity of slab column connection. And similar to shear, Annex L incorporates the fiber contribution through this additional resistant term, but in this case, only 40% of this contribution is considered in the formulation through this parameter of eta F, which is 0.4 in this case, instead of 1, which was the case of the shear. In addition, the code introduced the interaction parameters to account the fact that the fiber contribution, as in the previous case, is not fully additive to the concrete or reinforcement contribution. If we move to the serviceability limit state, one of the more recognized benefits of steel fiber reinforced concrete is the ability to reduce crack spacing and crack widths under service conditions. So in Annex L, this effect is mainly introduced through the modification of the mean crack spacing formulation used for the plain concrete. So depending on the reinforcement arrangement, the code distinguishes between multi-cracking patterns and single crack patterns. In the case of multi-crack patterns, the mean crack spacing is reduced through a parameter accounting for the crack arresting effect provided by fibers. So beyond all these code provisions, there are still several practical aspects that remain particularly relevant for the structural application of fiber reinforced concrete. Among them, one of the most important challenges is probably the characterization and quality control of the post-cracking behavior of the material. One of the main challenges associated with fiber reinforced concrete in general is the intrinsic scatter affecting its residual tensile properties. This variability is related to several sources of uncertainty associated with the testing procedure itself, with the production process, and also the intrinsic variability of the material. In particular, the residual strength of fiber reinforced concrete strongly depends on the amount, distribution, and orientation of fibers crossing the crack area in the test. So for this reason, for example, in the case of the 3-point bending test, the results might have typical scatter between 10 and 30%. An important point is that this variability is usually more significant at material level than at a structural level, where larger resistant volumes tend to produce a more stable global response. So in this regard, although Eurocode 2 does not explicitly refer to alternative testing method, this procedure may be used for quality control purposes, provided that a statically robust correlation is established between the 3-point bending test and the alternative test method. One example of this alternative test method could be the double punching test, also known as the Barcelona test. Compared to the conventional 3-point bending test, this methodology presents several practical advantages because we use smaller specimens, simpler experimental setups, and easier execution under production conditions. But the most important one is that the larger fracture surface involved in this type of test reduce part of the scatter associated with the characterization of the residual properties. But it's important to note that this alternative procedure can only be used for quality control, and once a robust correlation between the 3-point bending test and the alternative test is established. So related to once we have passed through the quality control, if we move to the application of the real structural application, one representative example of application are the flat slabs. So the use of fiber reinforced concrete in flat slab has been extensively investigated through full-scale experimental studies, but also real building application. One of the main objectives when we use fibers in slabs is the partial or even the total replacement of conventional reinforcement, together with improvements in the construction process itself. In particular, the combination of fibers with self-compacting concrete allows avoiding vibration during casting, reducing the potential reorientation of fibers, and improving the execution process on site. So, although fiber reinforced concrete solutions are usually associated with higher direct material cost, experimental studies and real application has demonstrated that important reductions may be achieved in construction time, labor requirements, and indirect cost. But however, the discussion is no longer limited to the structural performance or direct cost. The question is, how about sustainability? How is it considered? Well, so in recent years, sustainability has become an increasingly important aspect in the assessment of a structural solution. In this regard, the FIB Model Code 2020 adopts a broader definition of sustainability based on environmental, economic, and social aspects. And to account for these different dimensions simultaneously, multi-criteria decision-making methodologies are required. One example of this could be the MIBES proposed within the FIB framework, which allows aggregating different sustainability indicators into a global sustainability index. And this methodology has already been applied in the several FIB documents related to precast and fiber reinforced concrete structures. In this context, sustainability assessment has already been performed for real fiber reinforced concrete building application. And here we have an example, with this example shown correspond to a real office building where different structural alternatives were comparatively assessed. The study considered a conventional reinforced concrete solution together with different steel fiber reinforced self-compacting concrete alternatives with reduced reinforcement, which is alternative 2, or without it, which is the alternative 3. So based on the sustainability framework, our requirement 3 was defined including environmental, economic, social indicator, and the different indicators were assessed for the different alternatives. The results show relatively similar global sustainability performance for conventional reinforcement concrete and for the hybrid solution of fiber reinforced concrete. However, the alternative with a significant reduction of conventional reinforcement presented the best overall performance. The main improvements were associated with the construction-related aspects, including faster execution, reduced noise during construction, and lower impact on the surrounding environment. So overall, all these results highlight the potential of fiber reinforced concrete, not only from a structural perspective, but also regarding construction efficiency and sustainability. But apart from building application, fiber reinforced concrete has also gained a significant relevance in underground structures and tunneling engineering. Actually, tunnel linings probably represent one of the most consolidated structural applications of fiber reinforced concrete. In underground structures, fibers contribute not only to crack control and durability, but also to the structural resistance associated with transient load conditions during the molding, storage, transportation, handling, placing, which may become governing in many practical situations. In fact, for a small diameter tunnel and moderate loading conditions, fibers may even provide sufficient reinforcement capacity without requiring additional conventional reinforcement. So the structural application of fiber reinforced concrete tunnel segments has been extensively investigated through experimental studies, numerical analyzing, but also real tunnel projects. In this regard, the FIB Bulletin 83 provides a comprehensive overview of the design principles and practical application of fiber reinforced concrete in precast tunnel segments. But one particular relevant aspect in underground structures is the structural response of the materials, and particularly for fiber reinforced concrete when we are under fire or after a fire exposure. So fire represents one of the most relevant or severe accidental loading situations for underground structures and tunnel linings. Under elevated temperatures, concrete experiences a progressive degradation of its mechanical progress, while in the case of the fiber reinforced concrete, the post-cracking behavior must be considered. Although the new generation of the Eurocode 2 already incorporates a specific recommendation for fiber reinforced concrete subjected to high temperatures, the available experimental evidence is still relatively limited, and further research is required, particularly regarding the residual post-fire structural behavior of fiber reinforced concrete members. So in this context, I want to share with you our research group at UPC, together with other companies, is currently involved in the project Digitune. It's a research project in which we are developing large-scale experimental campaigns conducted to evaluate the residual capacity of fiber reinforced concrete after fire exposure for different fiber types, different contents of fibers, and also different temperature levels. So this is all. Thank you very much for your attention, and I would also like to thank you again the FIB Young Members Group and the RILEM Youth Council for the invitation and for organizing this webinar.